Hi everybody, let me first prepare the desktop. In this video, you will learn the meaning of differentials and you will learn how to compute them. I hope you already looked at the PowerPoints regarding linearization that I gave you, and let us start with reviewing the main points. Okay, so if we have a function, let me see, on this picture we have a curve. It's a function, I'll call it f of x, and we also will have a tangent line at one point. We will give it a name L. That will be line, tangent line. It's also a function. You can clearly see that near x, the line L and a curve are very close to each other. Okay? I will call this point P, and if we move that point, we can move it along f function and along L, its tangent line. So, we move P either along F, or we can do that along L. And once we do that, we can create two different points. Let's see, this and this. The horizontal change, horizontal change will be denoted delta x when it's along f function and dx when it's along L function. So in this case, we moved horizontally by, call it delta x, and we'll put it, that will be the same distance dx. The corresponding vertical distance, vertical change, we will write here along f delta y and along L dy. Okay, so as we move point P, we shift this to the new location. The changes that will occur horizontally and vertically, we will call them delta x and delta y. If we are looking at the changes when the point moves along a tangent line, we will call them dx and dy. So I will just denote dy, this distance here. Okay. What is the distance? Delta y is the distance from the y of point P to the y of the point after the shift. So that distance will be delta y. Okay, so in all this construction, we want delta x and dx to be exactly the same. So horizontally, we move point P from x into the new value x plus delta x, which is the same as x plus dx, because delta x and dx are the same. It's a horizontal shift or horizontal change. However, we can see that depending whether the point moves along the function or along the tangent line, the delta x and y, I hope you see they are not the same. So, however, if that changes delta x, which is the same as dx, if that change is small, we can see that delta y is not that far from dy. It means if delta x, if we will be very close to point P itself, we will move just slightly to the right or left, delta y and dy are very close because L is very close to function f. So what is change in y? When we move point P into its new location, change in y direction is f of x plus delta x minus f of x. What is dy? It is vertical change given from a line. L of x plus delta plus, I will call it dx, minus L of x. Okay. And that's why those dx and dy are called differentials. How to compute differential? You can see this dy, this Lx plus dx minus L of x, you can have it, but that's not the way we usually compute this. To have different formula, I want you to tell me what is the slope? The slope of L. Okay, let us write this. It's m. It's a slope of the tangent line. So I hope we all remember that the slope of the tangent line is the geometric interpretation of derivative. If we compute f prime of x, that's the slope of the tangent line. On the other hand, this is slope, so it is a slope of the line, so we already know that will be rise over run. For our line L, it will be dy over dx. Okay, and here we have that link that I want to explore a little more. So since f prime, f prime of x is dy over dx, when dy and dx are those changes taken from the tangent line, but we see that ratio of dy over dx is the same as derivative. This is the why we are using dy dx as alternative notation for f prime of x. It is the same. They will give us exactly the same. And when we write this equation in a different form, dy is equal f prime of x times dx. That's what is the definition of differential dy. So if f equal f of x is a differentiable function, then the differential dx and dy, they satisfy. That's the condition I wrote above. So before we go more into meaning of the differential, let us just use that formula to evaluate, to find differentials. So if y is equal sine of x, dy is equal cos of x, f prime of x, times dx. Okay? You can think about this formula as dy dx derivative is equal cos x, and just to move dx to the right hand side of the equation. Okay, you will use this computation a lot in your second calculus course, so it's very easy. If you know derivative, you can easily write differentials. So if in the second example here we have y is equal tangent theta, so dy, differential dy, will be derivative of the tangent is secant squared theta. We don't have our variable is called theta, we write it as theta. Okay, so if u is cosine x, differentials will be called du. minus sine x derivative dx. Always you can write first derivative dy dx and then bring dx on the other side as in a second step, or try immediately. So what is here a differential du is cos of e to the power x times e to the power x. Chain rule, derivative of outside function, keeping inside unchanged, times derivative of the inside function. That will be derivative, that will be du dx. To have a differential, we need to put dx on the right hand side. So I hope right now you can compute differentials very easily. As I told you, you will know in this after watching this video how to compute differentials. And if you know how to compute derivatives, you know how to compute differentials. But what is the meaning of differential? It's still, I would like us to explore it a little more. So let us look at this example. If we have a function y, which is the area function of a square, a is equal x squared is the area of a square. What does dA differential represent? Okay, so let us look at two different pictures. We start from the function. So if we have a function, it's a parabola, it's actually the same that we had before. This will be our function a of x. For x equal, for given value of x, x is the side, length of the side, we can compute, by squaring a, we can compute the area. It will be x squared. Now, if we increase x by delta x or dx, okay, so we'll put the next point, x plus delta x, x plus dx, which is the same, we will move that point. If we move along the line, we will have different point, and when we move along the curve, different one. Okay, so the distance horizontal changes delta x, which is the same as dx, and what is the here value is delta a. The value taken from the tangent line means this one, that's dA. So if a is equal x squared, we can compute what is dA. Do you know what it is? dA will be 2x dx. We already know how to compute this. So if we have a graph of the function, it's a parabola, a of x equal x squared function, dA we will see for any x and any dx, we would see dA a vertical shift, but measure up to the tangent line, not the original function. Okay, but what if we are not looking at a graph of quadratic function, but an actual square? What it is? Now think about a square of a side x, x, and you will have the original, the smaller square. Right, let me look at that. Okay, so this is the square. Maybe I will put there some color. If to x we add extra length, delta x, or you can call it dx, this extra length is here and here. Okay, that will give us a bigger, if we add this, delta x or dx, delta x here equal dx, it will give us a bigger square. So what is delta A? Is increase in area. Maybe change in area. change in area or additional area. What color will we put for this? Maybe green. Okay, so all that additional area is delta A. Okay, if length x is increased by delta x, the area is increased by delta A. That will be delta A. Now, what is differential? What other? I will put the differential dA, which is 2x dx. Think of this, it's x dx plus another x dx. Okay? We will see it as two rectangles. X, the original x times dx, it's this rectangle, and again x times dx, this rectangle. You see that delta A is very close to dA. Okay? dA, that 2x dx, approximate delta A. Okay? The difference is that little, okay, this small green square in the corner. Okay, so if we see a function, delta A, and dA are the length of the graph. If you see an actual square, what is dx is that additional length. Delta A is the total change in area. dA is approximation, very close to delta A, and we can compute differentials. dA is derivative of A times dx. Okay, so let us look at our last example for this class. We have the sphere of a radius 10 millimeters, and we have a measuring error. We will call it delta R or dr. It will be the same, and it will be 0.1 millimeter. Okay, and what we want to compute volume, which is 4/3 pi r squared, and it's very easy. We can, of course, plug r equal 10, and we will have r cube, 4/3 pi r cube, 4 10 to the power 3,000 pi over 3 is the corresponding volume. But what is corresponding error in volume? The error in measuring radius will result in having an error in volume. So what is that delta V? Okay, we will approximate this with dV, differential. So if V is 4/3 pi r cube, what is dV? dV is 4/3 pi times our variable is r, 3r squared dr, and by replacing the value, r is equal 10 and dr is equal 0.1, 3 will cancel. We will have 4 pi times 10 squared times 0.1. It will be in millimeters cube, and which is 40 pi millimeter cube. Okay, so that's what the is equal 40 pi millimeter cube. Okay, so that's the resulting error in volume. That's what we found. It is approximation of it using a differential. And the last thing, the relative error will be just that delta V or dV over total V, which will be here we have 40 pi over 4,000 pi over 3, which will be 3, the pi cancel, 4 cancel, 3 over 100, which is 3%. Okay, so this error and measurement of the radius give us 3% possible the error in total volume. Okay, so thank you. That was the last part. Let me just stop recording quickly.